Let's begin by taking a look at two similar but still different situations. Let's say we have two objects. Both of them have mass m, and they're both at rest on top of similar planes that are both height. They're both a height h above from the bottom, and the angle of both planes is some angle theta. Okay, and then let's say we let both of them go. Well, we know that in time, we'll say that the top plane is frictionless, but then we'll say that the bottom plane has friction. The difference is the mass on top is just going to slide down the plane. And so when it gets to the bottom, it's going to have some speed v1. Whereas the second mass, even though it's the exact same mass, it's going to be rolling. And so it's going to get to the bottom and it's going to have a speed v2. And so let's say we actually go out and we perform this experiment. What we would see, so you probably remember from before that v1 is the square root of 2gh, and so that's if we solve this using conservation of energy. So, is v2 equal to v1? In other words, if I have one mass sliding down, if I have another that's rolling, when they get to the bottom, they have the same speed? And the answer is no. No, they don't. In fact, what you would find if you calculated this, if this was, for example, let's say that this was just a spherical ball, we would see that v2 is actually the square root of 5/7 v1. So in other words, in the case of the sphere, the velocity is less than, a rolling ball has a slower velocity when it gets to the bottom than a sliding mass. But let's think about what that implies. Remember, we're saying that energy is constant. So they both started with the initial energy mgh, right? In the case of v1, we just said that that's equal to 1/2 mass times v1 squared, so v1 is square root of 2gh. In the case of the spherical mass, though, this is equal to 1/2 m v2 squared plus something else, right? Well, there's no work being done on the system. So this doesn't have to do with work. There's no energy lost. So what that means is we have another type of energy. And this is rotational kinetic energy. And so that's what this unit's about, is we're going to see how we can calculate what the rotational kinetic energy is so that we make sense of this missing piece of information.